Hi everyone, and welcome to a nice short video on the factor theorem, which is again leading on from the remainder theorem, a very key principle of polynomials that you'll study in year 11 or year 12. So the first thing to note about the factor theorem is its definition, and it's actually quite logical when you think about it a little bit. But if we have z take k as a factor, then the p of k is going to equal 0. So think about what factors are. You've probably heard factors before. So again, if we factorize a quadratic, we have two factors generally, or a repeated factor, equal to 0. And from that, we know that if we were to, we can set that expression equal to 0. So we could set, in this case, z take k as a factor equal to 0. And we could actually work out that z would equal k to satisfy pk equals 0. Have a little bit of a think about that. Hopefully it will make a little bit more sense after the example, but that's really what the factor theorem is saying. So if you remember the remainder theorem, the factor theorem is really, in fact it's probably even easier than the remainder theorem to understand. So let's have a look at a problem and then we'll come back to that idea there. Show that z take 2 is a factor of p of z equals, and we've got a polynomial here, we're using z's in terms of x's. Really, that's just a notation thing. We generally do that because z could be any input we want. It doesn't have to be a real number. It could even be a complex number, for example. But we're going to deal with real polynomials for a moment. A polynomial that has real coefficients. But what we essentially have is a polynomial. I won't read it out, but it will work for all values of m. And we want to know for which value of m we actually get a double root, z take 2 squared. So you may remember a double root, a repeated root, is, if you remember maybe if you've done year 11 mathematics, when the discriminant is equal to 0, we have it touching the x-axis. That's really what a double root is, and we want to find for what value of m we get that double root. But let's have a go at the problem first, and we'll come back to those key ideas. Quite a bit of conceptual stuff here, hopefully remember it from previous mathematics. If this is your first time learning it, it might take a little while to sink in, but we'll go through it. So z take 2 equals 0. That's what we would have if we have a factor. Really, I'm just showing that that means that z equals 2 causes p of z to be 0. So really, the p of 2 equals 0. So if we substitute 2's into this cubic, then we're going to get 0 as the answer if we substitute in 2's for all the z's. So if p of z is a polynomial, we can divide it by its factor z take 2. That makes sense. We can divide any polynomial by its factor and we can expect no remainder. So we're going to use a process known as synthetic division. Hopefully you've come across it before. If not, that's okay. But we bring the 1 down. We essentially write the coefficients of the cubic across the top line. So from the problem, 1 is the coefficient of z cubed. Then we have m for z squared. 3m take 2 for z, and then our constant is negative 10m take 4. So really all I've done is I've just listed the coefficients in a line there. Really simple. It's literally just copy paste. And what I'm doing now is I'm bringing down the 1. This is synthetic division. It's really simple. It is so routine, but it's so amazing. And really we're doing it because we have a linear factor z take 2. I wouldn't be doing this if I had a quadratic. I'd have to do polynomial division. It would take me a lot longer, but synthetic division is amazing. It really is. What I've done, also linking in here, for synthetic division to work, I need to actually rearrange this so that I get 2 out as my result here. Because it said take 2 equals 0, I need to make sure that I actually have the negative of whatever that constant is as the value there for my division process to work. I won't go into any detailed reasoning behind that, just trust me. But we bring the 1 down, we multiply the 2 and the 1, so I brought the 1 down to the bottom bar here, 2 times 1, 2. Bring it up to this position here. That's how I got my 2 there. Then what I do is I add these two, m plus 2. And then, really simple, again I multiply it by 2, and I get 2m plus 4, and I put it in here. So this row gets filled in as I complete the synthetic division. Then I add these two together, 3m plus 2m, 5m, 4 take 2, it's obviously positive 2. And then from there, I double this, times this by 2 again. And, whoa, I get 10m plus 4. But my constant was negative 10m take 4 from my cubic. This means this last value is 0. And this last value in synthetic division is always a remainder, so we've got 0 remainder, so it's a factor for any value of m. I could put any value of m in there, and I would have no remainder from dividing it by that linear factor. That is pretty cool. So we've just shown that. We've done the first half of the question. We have shown that. Hopefully that makes sense. Synthetic division, you just need a little bit of practice. Really, it's quite routine. But now, let's look for a very special value of m, the one that causes a repeated root. So there are 3 roots to a cubic, 2 for a quadratic. But because we have 3 roots, we know that we're essentially, if we have z take 2 squared, that's 2 of our roots and we have 1 more. And again, because we have a repeated root, we know that what we can do is we can just take this result here from dividing it by z take 2 once and divide it by z take 2 again and see what happens. Really, that's all we need to do for a quadratic, because we can divide it by any linear factor and the factors will all come out nice and simple, because again, we can have 3 factors in this case. That's very important for later on. I won't jump to that straight yet, but all I've done is I've taken these results. This is a quadratic here. This is x squared plus m plus 2x plus 5m plus 2. There's our constant on the end, 5m plus 2. And what that actually means is that that quadratic there is a factor. So linear factor, quadratic factor. But we can break this quadratic factor down into another linear factor if we want. And that's what we're going to do, because we want 2 linear factors. Hopefully this is starting to make a bit of sense. Practice is very key with this though. So we bring the 1 down. 2 times 1 is 2. We bring the 2 up to this position. Then we have m plus 2 plus 2, m plus 4. Then we times that by 2, we bring it into this last column, and 5m plus 2m makes 7m, 2 plus 8 is 10. And as a result, that's our remainder, and we have a linear factor here. So this is our last linear factor. We have these 2 linear factors, which are repeated, and 1 more linear factor. Our polynomial is 3rd order. It's a cubic, and we have 3 roots, z take 2 squared, and x plus m plus 4. Hence, that remainder that we got, that has to be 0, because we have nothing left. It's all gone. It's all, yeah, nothing. So we need to set 7m plus 10 equal to 0, and if that's the case, we just do the algebra. We bring the 10 to the other side, negative 10, divide by 7, m equals negative 10 sevenths to that repeated root. So hopefully this makes a bit of sense. Remember the factor theorem, again, if z take k is a factor, then pk equals 0. This is again a nice little neat question to think about cubic polynomials. Hopefully you enjoyed this video. Thanks for watching. Any comments? Leave them below.